Hi guys, Justin here from chemistrynotes.com, and we are starting a brand new section today, a brand new chapter, if you will. So this is section 16. Section 16 is titled Spontaneity, Entropy, and Free Energy. So we're going to talk about each of these guys separately. We'll then talk about all of them together, and we'll just kind of go into detail on what each means as far as chemical processes and chemical reactions. Now, you'll be happy to know in this section that we're finished with the ice table and we're all done with the whole equilibrium process. That covered sections 13, 14, and 15. So that was a tall order, and that's now behind us. So section 16 is spontaneity, entropy, and free energy. So let's just get started at the top of page 1 of today's notes. And I'm going to start off by kind of listing the first law of thermodynamics for you. This is we've seen this probably earlier, maybe in section 1 even, when I went over some of the fundamental laws. But let's reiterate it here. The first law of thermodynamics tells us that energy can neither be created nor destroyed. So the total energy of the universe is constant. Okay? Although the total energy of the universe remains constant, it can be interchanged between various forms, specifically potential energy or stored energy, right? And kinetic energy, which is the energy of motion. So a few simple, straightforward examples. Raising a book, right? If I raise the textbook up, right? That textbook in my hand has potential energy because I could drop it and convert it into kinetic energy. So if I were to drop that textbook, all that stored energy of the textbook in my hand, and then I drop it, turns into kinetic energy. So we're able to interchange between potential energy and kinetic energy. But the energy is always conserved. It's always the same amount in the universe, same quantity. Second example, and I will write a chemical reaction out here. This is a combustion of methane. CH4 gas plus 2O2 gas yields CO2 gas plus 2H2O plus energy is released. Okay, anytime you combust a carbon-hydrogen compound, it's going to be exothermic, right? So heat is released. So it says here, the reaction releases energy in the form of heat. So that heat, or that release of energy, is not lost and gone forever. That heat is then somehow, somewhere, it's going to get reutilized in the universe. And the blurb underneath the boxed up equation here says, the reaction releases energy in the form of heat. The energy flow results from the lowering of potential energy in the bonds of the reactants. So some of the stored energy in the reactants is then converted into kinetic energy, as we see in the exothermic reaction. So I just wanted to do a quick blurb there on conservation of energy and the differences in potential and kinetic energy. Now, just a note here, at the top of page 2 of our notes, it says, the first law of thermodynamics tells us not a single thing about whether a process is likely to occur or not. So the first law of thermodynamics tells us nothing about whether a process, in other words, whether a chemical reaction is likely to occur or not. Spontaneity is what tells us this, okay? So we're going to lead up to spontaneity. Most of today's video, I'm going to talk about something called entropy, which has the symbol capital S or delta S. But spontaneity is where we're heading in this section, okay? Spontaneous processes and entropy. A process, in other words, a chemical reaction, is spontaneous if it occurs naturally, all on its own, without any outside help or any outside intervention, okay? So a process, if you just set up a chemical reaction and leave it alone, it'll happen all on its own naturally. We don't have to interfere with it. We don't have to give it some oomph. We can leave it. It'll take its course all on its own in the forward direction. Now, spontaneous processes may be fast or slow, but they do occur naturally all on their own without any outside help or intervention. Some spontaneous processes include the rusting of iron. Iron will rust naturally all on its own. Believe it or not, number 2, diamond. The diamond that you're wearing, or the diamond that your friends have, or the diamond in your neighbor's ear, that diamond is slowly being converted to graphite, but that process is so enormously slow that we really never would see that. It takes like millennia for a diamond to convert to graphite. Number 3, heating. Heat flowing from a hot object to a cold hot object. That's a spontaneous process. Number 4, ice melting above 0 degrees Celsius. That happens naturally all on its own. So 1 through 4 there are spontaneous processes. What makes these processes or these reactions spontaneous? Well, at the top of a new page of notes here, it says the following on this little bullet point. It says each process, or each chemical reaction, if you will, occurs with an increase in entropy. So what is entropy? This is a new term for us. I got a double underline under it. It says entropy, S. That's a capital S. Entropy is defined as a measure of the randomness or disorder of a process. Okay? The natural tendency of things in the universe is for there to be more disorder. Okay? It's very difficult for you to organize your room. You can only organize it and clean it up in a few specific different ways, but there's an infinite number of ways in which your bedroom can get messy, right? And spontaneously, your room has a tendency to get messy. And then we have to intervene and clean it up, right? And get it all reorganized. So entropy is defined as a measure of the randomness or disorder of a process. The natural progression of things is from order to disorder, from lower to higher entropy, okay? Now, in general, entropy increases in going from a solid to a liquid to a gas. There is more disorder in a gas than there is in a solid. So the solid having the least disorder, the gas is going to have the most disorder. And that's just because a gas, a sample of a gas, has more volume for the molecules to move around. So those molecules can arrange themselves in any way they want, okay? The larger the volume, the less order. Whereas a solid, okay, everything is nice and tightly packed into a solid, very dense, okay? Structured arrangements of particles, very ordered, very structured. So that has the least disorder. And of course, liquid is right there in the middle. All right, let's do an example. The example says, which has the higher entropy? So we want to find out which of the following has more disorder, more chaos, more randomness associated with it. Which has the higher entropy? So in the first one, A, we have carbon dioxide solid versus carbon dioxide gas. In the second one, we have nitrogen gas versus nitrogen gas, but different pressures. So in the first one, CO2. Okay, I don't know why I've just selected CO2 and not given you the state of matter. There's a typo on my behalf there, but higher entropy is going to be the gas. So the answer to A is CO2 gas. B, the answer is going to be the nitrogen that's at the least amount of pressure. Think about, look at my hands here. If I'm increasing pressure, volume decreases, right? Remember Boyle's law? So less pressure, here's me letting up on the pressure, right? More volume. If there's a larger volume, then the gas molecules are free to move around in more randomly associated ways. This larger volume means more disorder for a gas, okay? So it says less pressure corresponds to a larger volume, Boyle's law, PV equals K, which means N2 gas has more space to move around in if the pressure is less. So the N2 gas at 0.01 atm is our answer. Second example, predict the sign of the entropy change, delta S. Okay, that little delta means change. So we want to find out the sign of the entropy change. So first of all, if delta S is greater than 0, if delta S is positive, then the entropy is increasing. If my delta S is less than 0, well, then entropy is decreasing. All right? So predict the sign of the entropy change. We're going to do that on the next page. So let's get to our examples. The first one here is at the top of a new page of notes. A, solid sugar. Solids have very little disorder, right? Added to water. So a pure substance, sugar, is added to a pure substance, water, to form a solution. B, iodine vapor. So that's iodine in the gas phase. It's condensing on a cold surface. Now, we don't know if it's condensing to a liquid or to a solid, but in either way, it looks like the amount of disorder is going to go down. Let's take a look at A though. A, sugar molecules are getting dispersed into a larger medium, right? We're taking the nice structured, orderly, solid sugar crystals, adding them to water where they're all getting solvated or hydrated, right? So this is going to be larger volume, a larger medium for the sugar crystals to dissolve into. Disorder increases. Delta S is greater than 0 in this case. For B, I mentioned already that the vapor is going to condense. Now, it turns out iodine vapor will condense straight to a solid. It's really called deposition, right? Forms a deposit. But even if you didn't know that, just the word condense means things are coming down, smaller volume, smaller areas to move around. You're kind of forced to be more orderly or more structured. Disorder decreases and delta S is less than 0. All right, in the next video, we're going to continue talking about entropy, and then we'll start to get into these other topics of free energy, spontaneity. Delta H is even involved again. So we'll start off with the second law of thermodynamics in video number 2, which is coming up right now.